Hello friends, welcome back to this online certification course on watershed hydrology. I am Rajendra Singh, professor in the Department of Agriculture and Food Engineering at IIT Kharagpur. We are in module 1, it is lecture number 2 and the topic is precipitation. The course content of this particular lecture includes forms of precipitation, rainfall measurement. We will talk about rain gauge network design. We will discuss the radar measurement of precipitation, satellite estimates of precipitation, and we will also give an idea about the sources of rainfall data. Now, coming to defining precipitation. Precipitation is any form of water which could be liquid or solid that falls from the atmosphere to the earth's surface. That is, any form in which water is delivered by atmosphere to the land surface, as we saw in the hydrological cycle. Now, there could be various forms of precipitation like rainfall, glaze, snow, hail, drizzle, dew, frost, sleet. But out of these, rainfall and snowfall, these are the dominant forms of precipitation. Now, coming once again to different forms which we will be describing a little bit, starting with the rainfall. Rainfall occurs in liquid form with drop sizes varying from 0.5 to 6 millimeters, and it is formed by condensation of cloud droplets at temperatures above the freezing point. So, we have already seen hydrological cycle. We know that evaporation and transpiration or evapotranspiration occur. They take the water from land to the atmosphere where cloud formation takes place and then condensation occurs. The condensation of cloud droplet occurs at temperatures above freezing points, and then rainfall occurs in the form of liquid, and the droplet sizes are within 0.5 to 6 millimeter in diameter. Rainfall is classified based on intensity, and if the intensity of rainfall is less than 2.5 millimeter per hour, then it is called a light rain. If it is the intensity is between 2.5 to 7.5 millimeter per hour, then it is called a moderate rain, and if it is greater than 7.5 millimeter per hour, then it is called heavy rain. But one of the terms which we are quite often seeing nowadays is cloud burst. Quite often we see in news or read in newspapers that there is a cloud burst in say Uttarkashi or Uttarakhand or something like that, mostly in mountainous places. So, this cloud burst is a sudden and intense rainfall event, typically characterized by a large amount of rainfall occurring in a short period, and typically the intensity of rainfall during cloud burst could be greater than 100 millimeter per hour. So, that means it is a sudden and intense burst of rainfall, because of which flash floods occur, and lot of problems we come across in our daily news and so on, whenever cloud burst occurs in any place. Next important form is snowfall, which is precipitation in the form of ice crystals resulting due to desublimation, which is basically a process of phase change from gas, that is water vapor, to solid ice. So, that means because of desublimation there is a phase change, that is water vapors get converted into ice. Of course, the temperature has to play a significant role, and then when precipitation reaches surface in the form of ice crystals, then it is referred to as snowfall. And snow forms basically when the tiny icy crystals in cloud, they stick together to become snowflakes, and when enough crystals stick together, they become heavy and fall to the ground. So, basically snowfall is in the form of snowflakes of varying weight, or the weight is important because when they are heavy enough, then only they fall to the ground. Then the third one is drizzle, which is basically a form of rainfall where precipitation occurs in the form of water droplets, but the droplets are less than 0.5 millimeter in diameter and intensity is less than 1 millimeter per hour. So, that means Basically, a rain event occurs with drizzle many times, unless it is a sudden event, and with drizzles, and then it takes it becomes stronger and takes the shape of a rainfall. The other form is dew, which occurs because of the condensation of atmospheric moisture or water vapor that forms as tiny droplets on surfaces like grass, leaves or other objects. So, basically in the winter evenings or mornings, we often find lot of water droplets on different objects like grasses or leaves. So, this is nothing but dew. Hail is the precipitation in the forms of lumps of ice which have a size of more than 5 millimeter diameter, which is primarily formed due to alternate freezing and melting. So, hailstorm also comes, but that is only during certain specific season. Then glaze is again very common in places, the colder places, where ice coating formed when raindrop freeze while they come in contact with cold objects on the ground. So, basically if you are at a colder place, and if you go outside during winter season, you will find that any metallic object, most of the metallic objects, they will have some kind of a ice formation, and that is nothing but glaze. Then another important form is fog, which is nothing but a low lying cloud, which is composed of tiny water droplets or ice crystals suspended in the air near the earth's surface. And again, fog is a very common phenomena during winter season. Another form is sleet, which is frozen raindrops or transparent grains which form when rain falls through air at sub-freezing temperature. So, if when rain falls and the atmospheric temperature is sub-freezing, then gets converted into ice, or it gets frozen and then it falls in the form of sleet. Now, coming to types of rainfall, we have 3 major types of rainfall. The most common is of course the cyclonic form of rainfall, which is basically a counterclockwise rotation of air masses resulting in low pressure in the center, which is referred to as cyclone or low pressure system. So, basically because of this clockwise rotation of air masses, which results in the low pressure in the center, what happens, this low pressure, this sucks the air from around, that is the wind converges to the center, and they are driven vertically to colder altitudes where conditions occur. So, they are sucked into this center and they are taken vertically up, where to cooler temperatures, where they get condensed and the rainfall occurs. And of course, you know that cyclones bring heavy rainfall to area, and their coverage is also large. The coverage could be as much as 2,500 kilometers in diameter, and they move fast, and typical movement is 50 kilometers per hour. It could be much larger, we will see in a minute or so. Now, tropical cyclone is very common in tropics, and in India we keep on getting many a times, typically formed over warm water bodies, that is oceans, when the ocean temperature goes certain level, and say for example, Indian Ocean or South Pacific Ocean. And then it basically in Indian Ocean and South Pacific Ocean, it is called as a tropical cyclone. It is in other places, it is known in other names. For example, in Atlantic Ocean or Northeast Pacific Ocean, it is called as hurricane, and in Northwest Pacific Ocean, it is typhoon. So, basically hurricane, typhoon and tropical cyclone, they are all types of cyclonic rainfall. And as you know that in coastal regions, our country, cyclones are very common phenomena, and when they come, they cause havoc if no proper care is taken. So, that is why the India Meteorological Department, which basically takes care of our forecast cyclone, they have classified cyclone in different classes, like based on the movement or the wind velocity. If it is between 62 to 87 kilometers per hour, then it is referred to as cyclonic storm. 88 to 117 km per hour, it is severe cyclonic storm. 118 to 167 km per hour, very severe cyclonic storm, and if it is greater than 222 km per hour, super cyclone. So, basically whenever cyclone occurs, we always hear about whether these terms, that it is going to be a very severe cyclonic storm or severe cyclonic storm. These are all defined based on this classification which is provided by IMD. Now, another form of rainfall is convective, which is basically, in the previous one it was because of pressure, and in this case it results due to heating of earth surface that causes air to rise rapidly. The rising air cools and condenses, resulting in precipitation, and it occurs mainly in equatorial regions, and in India whatever pre-monsoon rain we get, it is because of the convective form of precipitation. So, basically in this case also the process remains the same, that the air gets lifted and condensation occurs. Only thing is that in the cyclone it is a low pressure system which sucks the air. In this case it is the heating of the earth surface that causes air to rise rapidly. The third type of rainfall is orographic, which the name itself suggests, is basically linked to the terrain. So, basically it occurs in the mountainous areas, and it caused when air masses are lifted is a move over mountains of air. So, suddenly when there is a barrier, because of that the air moves to top, gets cooled, condensation occurs and rainfall occurs. So, that simply means in all three types of rainfalls, the basic process is the vertical movement of air to cooler temperatures, where it cools down, condensation occurs and rainfall occurs. Now, coming to measurement of rainfall, we typically use or rather rainfall is typically measured using a rain gauge, and rain gauges may be of two types, non-recording and recording type. And coming to non-recording type of rain gauge, Simon's rain gauge is the most common one, most popular one, and basically it consists of a vertical cylindrical container with top opening diameter of 127 millimeters. So, as you can see here, it is a vertical container and it has a top opening, and the diameter is recommended diameter is 127 millimeters, and a funnel shaped hood is inserted to minimize evaporation losses and to store water in an inner cylinder. So, as you can see in this figure, this is the outer cylinder having diameter 127 millimeters, and then there is a funnel inside this and there is a inner cylinder. So, this is the inner cylinder we are talking about. So, in this water gets collected, this funnel function is already known, that basically it is to minimize evaporation losses. So, when water gets collected, typical standard time of recording in India recommended is 8:30 a.m. So, every day at 8:30 in the morning, the recorder comes, empties this inner cylinder into a measuring cylinder and then records the rainfall, and that is recorded as the rainfall in the previous 24 hours. So, that is how a non-recording rain gauge functions. Coming to recording type of rain gauges, the mostly used recording type of rain gauge is referred to as siphon or float type of recording rain gauge. This also has a collection chamber and it has a hollow float with siphoning arrangement. It also has a clockwork mechanism with daily or weekly chart. So, basically as you can see here, this is how it looks, this one. Inside that we have a float, this chamber has a float, which I will just explain a little bit later, and then it has a clockwork driven mechanism, that is this drum over which a chart is placed, and this drum moves with the clock. So, that is how what happens when that water enters through the opening, rainwater passes through the lid or funnel, that is L here, it enters the cylinder or float chamber which is called, and then because of the change in the water level, this float here rises. To begin with, it rises, and the moment this rises, this recording mechanism which is attached to this records rainfall on this chart. As you can see here, when there is no rainfall, there is a horizontal line, but the moment there is a rainfall, there is a, because the water level rises. So, you can see that there is a rise, or here anywhere you can see there is a rise in the float, and that is being recorded by the pen on the chart. And of course, this has a siphoning arrangement, because siphoning occurs when the water level reaches a predefined level, S in this case. So, the moment water level reaches, and that is how these charts are calibrated. Typically, when 10 millimeters of rainfall, typically this is 10 millimeters. If when 10 millimeters of rainfall occurs, so this calibration is such that when 10 millimeter of rainfall occurs, siphoning takes place. And as you can see, siphoning, simply you see that the pen is coming back to the 0 level, and then again it starts recording. So, the advantage of this kind of rain gauge or recording rain gauge is that, as you can see, because siphoning takes place. So, it can record any kind of heavy rainfall during an event, and this is of course the most popularly used recording type of rain gauge. The other recording type of rain gauge is tipping bucket recording rain gauge. It basically consists of two containers on a balance beam which form the tipping bucket. So, as you can see here, these are the two tipping buckets. There is a beam on which they are balanced. So, when rain occurs, it fills one of the bucket which is just below the entry point of the water. It tips over, and then the rain is collected in the other bucket. So, the moment it fills, it tips, that is basically like seesaw, and it tips. Then second one starts collecting. When this fills, it tips, the next one comes, and the capacity of this bucket is manufacturer specific, that is instrument specific, but usually it is 0.5 mm. So, when 0.5 mm of rainfall occurs on one of the buckets, it tips, and then the next one comes into picture. And a recording mechanism which is usually digital, it records the data. That simply means that, as you can see here, a typical ticker. So, basically it records the number of tips of these buckets, and from there we can find out what is the magnitude of rainfall. The third recording type of rain gauge is weighing bucket recording type of rain gauge, which consists of a receiver bucket supported by spring or lever balance or some other weighing mechanism. So, there is the name suggests it is a weighing bucket, that means it functions based on some kind of weighing mechanism. It could be spring, which is the most commonly used. So, when a rainfall occurs, obviously the weight of this collecting bucket goes up, and that presses this spring, and this movement of bucket due to increasing weight is transmitted to pen, which traces a record on a clock driven chart. So, the clock driven chart mechanism is very similar to the siphon type of, but for siphoning impact, there is no siphoning in this case. So, it just keeps on recording. So, obviously from that perspective, it has a limited capacity of measurement. Now, coming to IMD's rain gauge network, IMD, that is India Meteorological Department, that is the custodian of rain gauge record or any kind of meteorological data in our country. So, they maintain a rain gauge network across country, and there are around 7,000 stations, and the station data of any of these can be collected from freely from this website. Based on this data, IMD also produces gridded rainfall data at 0.25 by 25 degrees resolution, and temperature data, because most of these stations also have temperature records. So, temperature data at 1 degree by 1 degree resolution. Now, this is the network, but as you can see that there are three major blocks of interest, A, B and C, which are here shown by a square or rectangle. So, in these areas IMD maintains dense range network for detailed analysis. So, it can analyze in detail what about the rainfall characteristics. Now, basically what happens that typically if you talk about a watershed, and if you say there is one rain gauge here stored here, and if you record the data, then this particular may not represent the rainfall over the entire catchment, because of simple reason that in comparison to the aerial extent of the storm or the area which we are interested in, the catching area of the rain gauge is much less, and that is why we need to have a rain gauge network installed in an area in order to get the representative image of the storm over the entire catchment. So, rain gauge network design basically aims at finding the optimum number of rain gauges and their location in a catchment. So, if you want to have a representative rainfall data for this particular one, the mean value, then we need to find how many rain gauges should be installed and where this should be installed. That is what precisely we do in rain gauge network design. Of course, there is a recommended network rain gauge network density given by World Meteorological Organization WMO as well as IMD. So, WMO recommends for plain area of tropical zone 1 station for 600 to 900 square kilometers, hilly area of tropical zone 1 station for 100 to 250 square kilometers, and polar zone 1 station for 1500 to 10,000 square kilometers. IMD has modified the recommendations. We have in plain areas 1 station for 520 square kilometer, regions of elevation above 1000 meters, 1 station for 260 to 390 square kilometers, and in hilly or mountainous areas 1 station for 130 square kilometers. Now, in rain gauge network design, we already saw that we need to find out the optimum number of rain gauges that should be installed in a catchment, and that can be estimated by this simple relationship n equals to CV by E square, where CV is the coefficient of variation of rainfall in the existing rain gauge network. So, suppose you have an area where you have certain number of rain gauges. So, you find out you collect the data from that and find out the mean and standard deviation of the data, and then we can calculate the coefficient of variation. And so, this CV basically is the coefficient of variation of the recorded data by the rain gauges already installed in the area, and E is the allowable percent error in the estimation of mean rainfall of the region. So, what percentage of error we want. So, obviously, if E value is high, the number will be lower. If E is lower, number n will be higher. So, if you want more precise data, you have to put more number of rain gauges. If you are you can settle down with little higher error, then this number could be risen. So, if there are m number of rain gauge stations in a catchment, each recording rainfall of P1, P2 to Pm during a storm, the coefficient of CV can be calculated. I mean, this is a statistical formula, that is a standard deviation by average, and standard deviation, of course, we can calculate using this formula, and mean we know how to calculate. So, where Pi is the rainfall at ith rain gauge station. So, using these data, as I already mentioned, that we need to calculate the mean of the rainfall and the standard deviation, and once mean and standard deviation is there, we can calculate the CV. We can take a simple example, that is, a catchment has 8 rain gauge stations. In a year, the annual rainfall recorded by the gauges in millimeter are 938, 1065, 1706, 1387, 878, 1562, 1809 and 1103. For a 10% error in the estimation of mean rainfall, we need to find the optimum number of rain gauges, and this question has been taken from GATE question paper of 2019. So, coming to solution, we know the rainfall magnitude. So, as already mentioned, we need to first calculate the mean rainfall. If you use the data, it comes out to be 1306 millimeters. We need to calculate the standard deviation, which comes out to be 359.17 millimeters, and then obviously we can calculate the coefficient of variation, which comes out to be 27.5%. And so, optimum number of rain gauge stations using this equation, the E value is already given 10%. So, by putting CV and E, it comes out to be 8, and fortunately, in this rate catchment there are 8 number of rain gauges. So, the catchment has the optimum number of rain gauges installed. Of course, there is another point is the location of rain gauge, which basically requires various kinds of statistical analysis. which we are not going into covering in this course. Then besides rain gauges, nowadays weather radars are very popularly used for measuring rainfall, and they basically, these radars work on the principle of reflection of energy, and they transmit radio waves in the microwave frequencies into the atmosphere. The frequency range could be 300 gigahertz to 300 megahertz, wavelength could be 1 millimeter to 1 meter. Now, when these micro radio waves are sent or transmitted, the beam hits solid or liquid particles in the atmosphere, basically hydrometeors, which could be in the form of falling rain, hail, snow, and some of the energy is reflected back to radar. And the intensity and frequency of the return signal and the elapsed time from the transmission of signal is measured, and then that tells us where and how much precipitation is occurring. Basically, for that these radars basically use reflectance, that is reflectance is nothing but fraction of reflected energy, and reflectance is used to evaluate the intensity of precipitation distributed in space and time over the area scanned by radar, and for that basically ZR algorithms are used, where Z is reflectance, R is precipitation, and A and B are constants. So, basically as you can guess that these ZR algorithms are location specific, also a particular instrument is specific. So, obviously there are several ZR algorithms, and of course their calibration is needed in order to adopt that. And the range of weather radar is approximately 350 kilometers. Now, in the radar measurement of precipitation, a big development is NEXRAD or next generation radar, which is a network of 159 high resolution Doppler weather radars, which are operated by National Weather Service, which is an agency of NOAA, that is National Oceanic and Atmospheric Administration, within the United States Department of Commerce. Now, the technical name of the radar is WSR-88D, that is Weather Surveillance Radar 1988, and it is a Doppler type, so WSR-88D, and it detects both precipitation and wind movement, and data basically is available in the form of mosaic map. So, it is a mosaic map for the entire area which is being scanned by the radar, and it operates in two basic modes: a slow scanning clear air mode when there is no rainfall, and a precipitation mode with a faster scan for tracking active weather. In India, IMD also has a Doppler weather radar network. There are around 37 Doppler weather radars. You can see these are the locations: Mumbai, Nagpur, and Gopalpur, mostly in coastal areas, and some of the major in between airports. And one such DWR Doppler weather radar is installed in Kailasgiri in Visakhapatnam, and you can see the picture here. Besides rain gauges and radars, we also use satellite estimates of rainfall, which are very useful for areas where gauge networks are inadequate or non-existent, that is over sea or hilly areas, or even ungauged basins. And basically satellites provide information in the form of cloud image. The cloud models are then used for interpreting this data. Now, in our country, INSAT satellite system is used for meteorological information, and of course, whatever information we see in the newspapers, newspapers, weather reports, or in television news, or in IMD website, you can always get these satellite images, which really tell you the movement of precipitation, so on and so forth. Currently, INSAT 3DR, which was launched in 2016, is the latest weather satellite used by India. Within the satellite estimates of precipitation, a major development has been Tropical Rainfall Measuring Mission TRMM, which operated between 1997 and 2015, which was basically a joint space mission of NASA and Japan Aerospace Exploration Agency, that is JAXA. to monitor tropical rainfall, and the term TRMM were used both for the mission as well as the satellite. And basically it provided measurements at a spatial resolution of 0.25 degree to 0.25 degree and temperature resolution of up to 3 hours. That means every 3 hours data were available. And first is the precipitation radar, the first space-borne instrument designed to provide 3-dimensional map of storm structure. Now, this operation was over in 2015. So, we have now a follow-up mission of TRMM, which is called Global Precipitation Measurement GPM, which is again part of NASA's Earth Systematic Mission Program. And basically it uses satellite constellation. That means several satellites of several countries are being used here. So, the participating countries are USA, Japan, France, India and European Union. So, satellites of all these countries and union are being used, and the data is available at a spatial resolution of 0.1 degree to 0.1 degree, and temperature resolution has been brought down from TRMM it was 3 hours, now it is available at 15 meters, and this also provides data in grid format. Now, before we close, I would just like to mention the sources of rainfall data. So, in India, observed data, we as already mentioned that from India Meteorological Department, this is the website. We can get station based as well as gridded data at 1 degree by 1 degree or 0.25 degree by 25 degree. 0.25 degree by 25 degree data is available from 1901 to 2022, where 1 degree is available at 1951 to 2022, and it is a daily data. Besides that, we have TRMM data. This is the website which is available from 97 to 2015, and then following 2015 we have GPM data which can be downloaded from this site. Besides these direct measurements, we have a multi-source weighted ensemble prediction valve also, which merges gauge, satellite and reanalysis data. It is provided 3-hourly time step at 0.25 spatial resolution over 1979 to 2017, and this is the website. So, you can freely download the data and do various kinds of rainfall analysis. With this, we close. Thank you very much. Please feel free to give your feedback and do ask questions on the forum or any way, so that we can answer that. Thank you very much.